How's it going, everybody? Mr. D here. In this video, we are going to be talking about exponential models, specifically growth and decay. So thus far, if we think of functions, right, we've learned about linear functions making straight lines. We've learned about quadratics. We've learned about cubics. We've learned about absolute values. We've learned about a whole bunch of these different functions and their shapes. Today, we're going to be looking at exponential growth. And what that means is that we have a graph that slowly increases, and then the rate of increase gets faster and faster and faster and increases more rapidly. Or conversely, maybe decreases more rapidly. If something increases, that's what's considered growth, and if it decreases, it's considered decay. So, let's get into some vocab. If you guys need to pause the video here to write this down, by all means, go for it. An exponential function is going to be written in the form of a times b to the x. So b is the base of an exponent. The variable has to be in the exponent for this to be considered an exponential function. We've seen functions with exponents before, but it's never been an x up here. Right? We've seen a squared or a cube, but never an x. So the base b is going to be some constant value. And we're going to learn later on, we're going to be pretty interested in the value of b. And then x is going to be the variable, the independent variable that will kind of determine our output for y. For growth, as x increases, the y value also increases. So here in blue, we have an example of growth. And for decay, as x increases, y decreases. So here we have, in red, an example of decay. Now you'll notice both of these graphs, and I'll zoom in as far as I can, but the image, resolution only gives me so far. These graphs get infinitely close to the x-axis, but they'll never actually hit it. They'll never actually touch the x-axis or cross through it. It's almost as if they're on, if you've ever driven on a freeway, it's almost as if they're on an entrance ramp that lasts forever and never actually merges, just gets infinitely close. The word for that line is asymptote. All right? And no, don't worry, I will not mark you off if you spell that word incorrectly. I realize it is a funky spelled word. Asymptote. Okay? Now, the way we can determine, just by looking at the function, whether it's growth or decay, is by looking at the base of the exponent. So again, that b value. And that b value is going to be one of two things. It's either going to be bigger than 1 or it's going to be smaller than 1. And I should make the clarification. Typically, we're going to see these as being positive values. So anything bigger than 1. So 1.4, 2, 17, 1.89. Anything smaller than 1, 0.5, 0.4, 0.3, whatever. So by looking at the b value, we'll be able to tell if a function is growth or decay. All right, so now let's take a look. And here we just want to find if we have something that's growth or decay, and then we also want to find the y-intercept. Okay, well, let's go first through, and we'll just identify growth or decay. Okay, so growth or decay is going to depend entirely on this b value, if it's bigger than 1 or if it's smaller than 1. So the first one, 17 over 10, that's 1.7. That is clearly bigger than 1. That would be growth. 5/6. 5 divided by 6 would be less than 1. That would be decay. 6 is clearly bigger than 1, so that's growth. 0.65 is less than 1, so that's decay. 1.63, that's bigger than 1, so that's growth. And 4/3, 4 divided by 3 is bigger than 1, so that's growth there. Now, when we're finding the y-intercept, we have to keep in mind the fact that the y-intercept always has an x value of 0, right? So whatever the y value that comes out of that is our y-intercept. Now I'm going to use number 1 here as kind of example, and we're going to see a pattern here. But if I were to write number 1, so we have 12 times 17 tenths, and I wanted to plug in 0 for x, well, if we remember our exponent properties, this whole thing just becomes a 1. So I really have 12 times 1. So that's just 12. Generally speaking, your y-intercept is always going to be the a value from that standard form. Because if I plugged in 0 for x, that b to the x power, b to the 0 power, just becomes a 1. So we're left with just that a value. So the y-intercept for number 2 here would be 0, 4. The y-intercept on number 3 would be 0, ooh, there's technically a 1 chilling out there. So 0, 1. For number 4, it would be 0, 2. For 5, it would be 0, 129. For 6, 0, 1/100th. So not too terrible. Let's take a look at word problems, though. You put $2,000 into a college savings account for 4 years. The account pays 6% annually. So it pays 6% annually. Well, if you're saving money here, I'd like to think that that would represent growth, right? Because you're retaining your original value of $2,000, but every year on top of that, you're getting a 6% growth. So this would be growth. Now the y-intercept is also going to be the starting value, and in this case, that would be 2,000. Number 8, you buy a car for 30 grand. It depreciates at a rate of 17% per year during the first 5 years of purchase. So growth or decay? Well, it would be decay. It's losing value. Bummer, but it's true. And then the starting value for the y-intercept would be 0, 30,000. All right, so that's just the basics of identifying growth versus decay, and then finding the y-intercepts. And when we have y-intercepts, that's actually going to help us graph these things later on. All right, let's get to graphing. We'll do a handful of these. We might be, well, depending on how quickly we go, we might be able to get through all of them. We'll see. We'll see. We'll cross that bridge when we get there. All right. So we want to sketch the graph of this exponential function by hand, identify the y-intercept, the asymptote domain, and range. Okay. Well, let's start off with this stuff over here on the right side. The y-intercept, the y-intercept is going to be this kind of a value, in this case, 0, 3. Which means, hey, I got a free point right there. That's pretty neat. And I could graph that as well, 0, 3. Sweet. The asymptote is always going to be the x-axis, which is y equals 0. So what that means is my function will never cross this x-axis, what I just put in black ink. The domain for every single one of these will always be negative to positive infinity, every single time. And then the range is going to be starting from the bottom and going up to the top, right? So if the lowest we ever reach is dang near close to 0, and we go up forever, this would be 0 to infinity. And that's always going to be the case for these until we start shifting the asymptotes up and down. Until we start shifting that asymptote up and down, it'll always be 0 to infinity. The 0 needs a parenthesis because we never actually hit 0 on the axis there. All right, so now let me get some extra points. If I plugged in, let's say, plug in -1 for x, well, 2 to the negative first is really 1 over 2, right? Negative exponents, we flip that, so 3 times 1/2. That's 3 halves. So -1, 3 halves, which is also 1.5. If I plugged in 1 for x, 3 times 2 to the first, well, that's just 6. So 1, 6. Now that I have 3 points, to the best of my ability, I'm going to connect these, and it's going to curve upwards, getting steeper and steeper. And as I go out this way, it's going to kind of shallow out and level off. So let's see if I can do that. And not my best, but also not horrible. All right, let's see another one. 2 times 1/4 to the x power. We need to get 3 points on the graph, and we also need to fill out these values. Hey-o. Now what I'm going to do is kind of cheat the system here, because as long as we're not shifting anything, these values for asymptote domain range, they ain't going to change. Right? They'll change when we shift things around, if we move it up and down, but until that day comes, those are going to be the exact same. So I just did a little self-plagiarism there. The y-intercept is going to be the a value, so in this case, 2. All right, now let's get to graphing. So we already know the y-intercept. We already know the asymptote, so it's never going to cross over that x-axis. Now let's plug in extra values. If I plugged in -1 for x, I'd have 2 times 1/4 to the negative first power, which is really 2 times 4, which is 8. So -1 comma 8 would be, I'm going to ballpark it, right up there. If I plugged in a 1 for x, 2 times 1/4 to the 1 power, that's 2/4. Well, that's 1/2. So 1 comma 1/2. So now I'd connect the dots. And there we go. We have an exponential decay graph. And logically, it kind of makes sense that this should be decay shape because, hey, we had a decay factor of 1/4, which is clearly less than 1. So in conclusion, for things that we've done today, and again, pause the video, take a picture, your y-intercept is always going to be the a value from the formula, so the number that does not have the exponent attached. Your asymptote, for now, will always be on the x-axis, y equals 0. So for now, it'll always be the x-axis until we start moving them. Domain is all real numbers, and then your range always ties in with your asymptote. So those always kind of go hand in hand. All right. I think we'll be okay without these examples here. If you need the extra examples, you guys always have access to these on the completed notes files available to you online. All right, so now let's take a look at an exit slip style question. Which function does the graph represent and explain? All right, so let's kind of unpack some information here. One thing I can tell you is that it's got a y-intercept of 0, 2, which means this should be 2 times something to the power of x. I know that so far. I'm also getting that this is a decay function because it's going downward, which means whatever goes in here has to be smaller than 1. So some fraction or decimal smaller than 1. All right, based on that, let's see what we've got. I need a 2 out front. Oh, I guess B is the only one that works, so it's going to have to be B. BB. It couldn't be C because that means our graph would have had to have been flipped upside down. So we would have kind of the mirror image of that if it were C. Okay. Next, we have a function, p of x equals 2.28 times 0.9 to the x, and can be used to model the number of payphones in millions x years since 1999. So a few things that I can get just by looking at this. 1, the y-intercept, 0, 2.28. The second thing, this is less than 1, so I know it's decay. In context of the problem, that probably makes sense, right? Payphones aren't really common anymore, so it makes sense that that number's going down. All right, so classify this function as either growth or decay. Already did that. Why can I not spell the word decay today? There we go. Determine what the y-intercept is. Already did that as well. 0, 2.28. And now, what does that mean in context of the problem? Well, the y-intercept is always the starting value, right? So the starting value was 2.28. But what does that mean for this problem? Well, we started in 1999, so it's going to be talking about the starting value in 1999. And it looks like we're going number of payphones in millions. So 2.28 million payphones. 2.28, I'm going to abbreviate, million payphones in 1999. Before you guys were even alive. Love you. All right. That is it for this video. You know the drill. If you have any questions, do not hesitate to ask. And as always, folks, good luck, have fun, be safe, roll tide.